Hi, Miss Patterson here. Today we're going to go over ionic bonds. This is part of physical science. So let's talk about chemical bonds. These are going to be the forces that hold atoms together, and it's going to be due to the interaction of those valence electrons. And if you remember, valence electrons are the electrons in that outermost ring, outermost circle. And when we talk about bonds, we're talking, and most of those are going to be due to that electron configuration, the electron pool outside. So a compound is going to be two or more elements that are bonded together. So let's review that real quick. They're going to be in a fixed ratio. And so when I have water, water's H2O. Every single water molecule I ever have will always be H2O. If I changed it for some reason and added another oxygen to it, and then it became H2O2, I would no longer have water. I'd have hydrogen peroxide. So my ratio changed, so my compound changed. So here I have water, H2O. This is what makes water water. If I change this, I no longer have water. I have chalk. This is my formula for chalk. If I change this, I'll have something different. I can see that I have a capital lowercase letter. This is calcium. Two capital letters, so this is carbon and oxygen. And remember, these are subscripts. These tell me how many of these atoms that I have in this molecule. I can show it out as a written formula, and I can also show it in a diagram. So here I have water, oxygen, two hydrogens, and here I could have something like methane or something. So I can have different models that can show compounds, but I can tell that there's two different atoms here, and that's the big thing with compounds. They're two different atoms bonded together. So here I have salt. This is sodium in its pure form, and this is chlorine in its pure form. When you see salt, it looks nothing like this. Salt is white, it's crystalline, it's you can eat it, it's not going to kill you, it's not going to blow up on you. But when they're separate, they're totally different. When they combine, a compound can change their properties. Another example is water. Oxygen at room temperature is a gas. Hydrogen at room temperature is a gas. Extremely flammable. But at room temperature, water is a liquid. Water puts out fires. So you use water to put out a fire for oxygen and a fire for hydrogen. But together they make water. It's weird. So a molecule is going to be any atom that forms a chemical bond. They can be different atoms bonded together. So here I have different atoms bonded. Here I have two that are the same, that are bonded together. But if there is a change of valence electrons, a change in charge that's bringing them together, that can create a molecule. So let's look at this. I want you to take a second and pause. And I want you to go back and let's refresh ourselves on a compound. Which one of these are compounds? These are compounds because I have different elements. I have nitrogen and hydrogen, oxygen and hydrogen, carbon and oxygen. These are compounds. Okay, these other ones are not because they're all the same element. So which ones are molecules? These are all molecules. So these are all molecules because there's more than one atom bonded together. I have more than one atom bonded together. I have more than one here, more than one here. Okay, these are all going to be a type of molecule. This is not a molecule. This is an atom because I just have one. This is an atom because I just have one. So let's look at our electron dot diagram. We also call this a Lewis dot structure. And for that, we need to figure out how many valence electrons we have in this diagram, because that is what you draw. You do not draw, remember our Bohr models, we drew all the electrons. This is a shortcut. And so this Lewis dot structure just shows the valence electrons. So to do that, we have to make sure we understand that these group numbers represent how many valence electrons I've got. So this group 1, my alkali metals, has 1 valence electron. Group 2, my alkali earths, have 2. For this physical science class, we don't really get into this transition group. So this 3 through 12, we just kind of ignore that for right now. This group right here, boron, this is going to be my boron family, and it has 3. And remember, we said the trick for this one is I hide that 1. And that 1 tells me how many valence electrons I've got. So this group has 3. This group has 4 carbon family. Nitrogen family has 5. Oxygen or the chalcogens have 6. My halogens have 7. And my noble gases have 8. The exception to this one, though, is helium. Because how many electrons does helium have? Helium has 2, but it's full. And so this ring is considered full. This column is considered full, so that's why helium is here. So helium is an exception to the 8. It has 2, but it stays in this noble gas column because it is considered to have a full shell. All right, so now we know which group number these are in. So let's look at oxygen. I want to draw the Lewis dot structure for oxygen, so I need to know how many valence electrons does oxygen have. Oxygen has 6. So how many dots would I draw around oxygen? 6. 1, 2, 3, 4, 5, 6. Let's look at calcium. How many valence electrons does calcium have? 2. So how many do I draw around calcium? 1, 2. I have gallium. 1, 2, 3. I'm in group 3. And that's basically it with this group. So you just look and draw out how many you've got. So remember over here, I have argon. I have 8. So how many dots do I draw for argon? I draw 8. So this is full. I can't add any more to this. This is my octet rule. Okay, we'll talk about that more here in a minute. So atoms want a full or empty outer shell. And this is the octet rule. What does oct mean? Oct means 8. So the rule of 8. So when I have a shell that has 8, it is considered full. It's considered happy. That's what I like to say. How many more electrons does an atom need to be happy? Those in the noble gases have 8, so they're happy. They don't want to take electrons from anyone else or give electrons away. They're happy in that. That's why they're so stable and what they call inert, very non-reactive. So atoms want to acquire 8 electrons in their outermost ring to become stable. They're going to become more stable when they bond and get these 8, or they're going to lose their outer ring. They're going to become more stable that way. So elements want to be stable. They want to be like these noble gases. So these elements are going to give and take electrons to mimic that. They're going to try to have 8 in their outermost shell. So how many electrons does phosphorus need to be stable? How many does phosphorus need to be happy? So let's look here at phosphorus. How many valence electrons does phosphorus have? It has, remember I cover up that 1, I have 5. So how many more electrons does phosphorus need to be happy? It needs 3. So let's look at our Lewis dot structure. I've written or drawn out my 5. 1, 2, 3, 4, 5. So I need 3 more to be happy. Okay, this is going to give me my full shell. I look at magnesium. Okay, magnesium is in group 2, so I have 2 valence electrons. How many more does magnesium need to be happy? I have 2, and I need to make 8. So how many more do I need? I need to bring in 6 more. But that's going to take a lot of energy for magnesium to have to pull in all of these electrons to gain the 6. It's going to be a lot easier for magnesium to get rid of these 2 electrons. These electrons are going to go into another atom, and it's going to bond with that one by giving those 2 electrons away. So now the question is, all right, well, I got rid of 2 electrons. I thought we wanted 8. I thought that made them happy. But let's look at magnesium. When I get rid of those 2, okay, here's these 2 in that shell. I get rid of them. What just happened? Look, how many electrons do I have in the outermost shell now for magnesium. 1, 2, 3, 4, 5, 6, 7, 8. Magnesium's happy now. It got rid of those 2. It now has a shell of 8. And so that's what is so good with these bonds. It's going to give those 2 electrons to somebody else to let them be stable. And this one here will be stable with its 8. So now it's considered to have that full ring. So let's look at carbon. Carbon has 4 valence electrons. So now let's think about this one. This is a little tougher. I have 4 valence electrons. How many does carbon need to be happy? It needs 4 more. So is it easier for carbon to bring in 4 or to have to get rid of 4? Think about that for a second. Okay, I can do it either way. I can bring in 4 or I can get rid of 4. It's going to take the exact same amount of energy. So let's look at sulfur. I have 1, 2, 3, 4, 5, 6. So it's in group 6. I have 6 valence electrons. Is it easier for sulfur to get rid of 6 or to gain 2? And this is kind of when I say kittens. Is it easier to get rid of 6 kittens or to get rid of 2? It's going to be easier to bring in 2. Or get rid of 2. So someone's going to get rid of 2 for sulfur to be able to have it here. So I'm going to bring in and gain 2 electrons. Let's look at beryllium. Is it going to be easier for beryllium to get rid of 2 or to gain 6? It's going to be easier for these 2 to go away than for it to pull in energy to bring in 6. So again, how is beryllium stable if I got rid of those 2 electrons? Let's remember kind of what we did with magnesium. But beryllium only has 4 electrons. So if I only have 4 electrons, how is that stable? I don't have 8 in the middle. So let's look at that. So here I have beryllium, and I'm going to get rid of these 2 electrons. That's going to be easier to get rid of those 2 than to bring in 6. And when I get rid of those, look what happened. Here I have my first ring, and my ring is full with 2. This is like helium, and beryllium's very happy to be like helium. So this first ring is full. Remember, that's why helium's in that noble gas column. So beryllium's first ring is considered to be full, so it's happy. So here we have carbon again. Is it easier to bring in 4 or get rid of 4? Either way I can do that. I can either bring in 4 or I can lose 4. It's going to take the same amount of energy for both. This is one reason why carbon likes to chain, and you can do so many different combinations with carbon, is because of this unique characteristic. So let's talk about an ion. An ion, remember, is when I have a different number of electrons than what's neutral on my periodic table. So it's a charged particle that either has more or less electrons than protons. So we have to look at our periodic table to figure out some information. So if I have some element that has lost electrons, I compare it to its elemental protons. If my number is different and I have less electrons, I'm going to be more positive. If I have an atom that has gained electrons, I'm going to be more negative. So let's look at lithium. Lithium has an atomic number of 3. So if I have 3, it's going to be 3 protons, 3 electrons. If I have 3 protons and 3 electrons, I'm neutral, right? 3 pluses, 3 negatives. If I have 3 protons and 2 electrons, am I more positive or am I more negative? I'm more positive by 1. If I have 3 protons, because again, remember, protons is what makes lithium lithium. If I change this number, I've changed my element. If I have 3 protons and 4 electrons, am I more positive or more negative? I'm going to be more negative by 1. So you kind of think of it that way, and if you have to write it out at first, it will click, but some people have to write it out at first so they can visually see that, and that's fine. So an ion is going to be between a metal and a non-metal, and metals are going to lose electrons. They're going to become positive because remember, I'm losing electrons, so I'm going to have more protons than electrons, so I'm going to be more positive. Non-metals are going to gain electrons, so I'm going to have more electrons than protons, so I'm going to become more negative. So let's look at salt. I have sodium. I have 11 protons and 11 electrons, and I am in group 1. So I'm going to have 1 valence electron. Remember, sodium doesn't want 1. It wants to get rid of it. It's very unstable. So it's going to want to bond with group 7. They have 7. They want 1. So they're going to be very happy to take this valence electron. And chlorine is going to do that very easy. So chlorine has 7 valence electrons. I have 17 protons and 17 electrons. So sodium is going to give chlorine an electron. Sodium is no longer going to have 17. I'm now going to have 18. I've just gained an extra electron. So am I going to be more positive or more negative? I'm going to be more negative by 1. Sodium had 11 protons and 11 electrons, but I got rid of an electron. So I no longer have 11, I have 10. So am I more positive at 11 or more negative at 10? I'm going to be more positive. So this is going to have a positive charge. And we call this an oxidation number. This is an oxidation number right here. So the positive and the negative number indicates how many electrons an atom has gained or lost or shared to become stable. So this is showing that they are sharing electrons or they've stolen electrons, they've transferred them. And now I have a charge. This change in charge, this opposite attraction, is what keeps sodium around chlorine and chlorine around sodium. It's like magnets. Negative opposites are going to attract. So those are your oxidation numbers. So let's look at this one again, and this is another way you can write it out. I have sodium. So I want you to look at your periodic table and find how many protons sodium has. Sodium has 11 protons and 11 electrons. So how many valence electrons does sodium have? So look at your periodic table. What group is sodium in? It's in group 1. So if it's in group 1, I have 1 valence electron. So is sodium going to want to get rid of that 1 electron or bring in 7? It's going to want to get rid of that 1. And if it gets rid of that 1, I'm no longer going to have 11 electrons, I'm going to have 10. So am I going to be more positive or more negative? I'm going to be more positive by how much? By 1. Okay? So I would write that out as Na1+. Starting out, you can write it like this, but you're going to see it most like this. If I don't have the 1, a number in front of it, it's inferred to be a 1. So Na plus is what I would see, and that's how you would normally write it. Starting out, if you need to do this to help you remember that, that's fine. Okay, does nitrogen want to get rid of 5 electrons or gain 3? It's going to want to gain 3. So now let's look at this one. Okay, I have nitrogen, so I want you to look on your periodic table and tell me how many protons nitrogen has. It has 7 protons, so it has 7 electrons. So how many valence electrons does nitrogen have? So look at its column. What group is nitrogen in? It's in group 5. So is it going to be easier to get rid of 5 or gain 3? And we said it's easier to gain 3. So now we have to figure out what charge is nitrogen going to be if I gain 3 electrons. So if I gain 3, I'm no longer going to have 7 electrons, right? It's going to be 7 plus 3, which is going to give me 10. So I have 7 protons and 10 electrons. Is nitrogen going to be more positive or more negative? It's going to be more negative. By how many? 3. Okay. So you'll be more negative by 3. So we write that out as 3 minus. We do a little minus here. And I can't just put a minus this time, right? Because I'm showing I have 3 electrons and not just 1. So let's look at sulfur. I want you to take a second and try this out on your own. So pause the video. So here I have sulfur. I have 6 valence electrons. Is it going to be easier to get rid of 6 or to gain 2? It's going to be easier to gain 2. So I'm going to look at my periodic table. Sulfur has 16 protons and 16 electrons when it's neutral. But I want to get rid of this unstableness that it has. So I need to bring in those 2 electrons. Remember, I'm going to gain 2 electrons. If I gain 2 electrons, am I going to be more positive or more negative? I'm going to be more negative by 2. So I would write this out as S2 minus. And if you're still kind of confused about it, think of it like this. I had sulfur. Sulfur has 16 protons and it has 16 electrons. But I brought in 2 more electrons, okay? So I'm going to have 2 more minuses, and that's where this is going to come in. So sulfur gained 2 electrons, so I'm going to be more negative by 2. Okay, beryllium, same way. I'm going to look here, and I have 2 valence electrons, so I want to get rid of those. And when I get rid of them, I'm going to have this shell full. Okay, so I'm going to be very positive because I'm going to have less electrons than protons. So here I have 4 protons, 4 electrons, but I got rid of 2. So that means I'm going to have a charge of a positive charge of 2 because I have more pluses than I do negatives. And again, another way to see it is this. I have 4 protons because that's what makes beryllium beryllium. And I have 4 electrons. That's what makes it neutral. But I got rid of those 2 electrons. So since I got rid of those 2 electrons, look, I have 2 more pluses than normal. And that's where that comes in right there. So beryllium is going to have 2 more positive particles. Okay, so now we look at carbon, and we have to write it out a little differently than those other ones. Because remember, with carbon, we said we can either gain or lose 4. It's going to take just as much energy for the other. So for me to do that, I can write it like this. Carbon can either gain or lose electrons based on whichever situations it's in. So I could write it out like this. Now, once I put it in a formula and I'm either gaining or losing, I have to say for sure what that carbon is doing at that time. So we have different types of ions. So remember, ions are atoms that electrons are more or less than your protons. And I have ones that are called cations. And cations are the positive ones. These are the ones that are going to be like sodium. It's going to be my plus is going to be after magnesium 2 plus, or I'm going to have a compound with a plus on it. This is telling me that I have lost electrons, so I'm going to have more protons, so that's going to give me a positive charge. All right, the best way I tell my students about this, and they remember it, is cations are positive, like a cat. Okay, they're going to be positive. So if you remember that, you'll always remember that cations are positive. All right. So then I have anions, which are like ants, and they're going to have little negative little antennas. And so these are going to be the ones that are going to be a minus. I'm going to have more electrons. So chlorine's an anion. And other compounds can be an anion with that negative charge. So an ionic bond, the force of attraction is going to be between those opposite charges. So I'm going to have potassium, and let's look at chlorine. Okay, I have potassium has 1 valence electron, and I have chlorine which has 7. So what's going to happen? Is chlorine going to want to take this electron, or is it going to want to give potassium all of its valence electrons? It's going to be easier to bring this in. So if it brings this in, I'm going to be more negative by 1 and more positive by 1. And that positive and that negative charge is going to pull each other together. And again, I have a metal and a non-metal, and that's going to be that ionic bond. So these opposite charges attract. So an ionic bond can gain or lose electrons. They're going to transfer. Sometimes they say they steal. They're going to keep it, and they're not going to be passing it back and forth. One's just going to keep it with it, and it's going to keep that charge. So let's look at salt. I have chlorine, which has 7 valence electrons right here. Okay, I have 7 valence electrons. And I have sodium, which has 1. Okay, here's sodium, and I have 1. So just looking at it, you can tell me what's going to happen. Is sodium going to want to get rid of 1 or bring in 7? Is chlorine going to want to bring in 1 or get rid of 7? So we know it's easier for chlorine to gain 1 electron than it is to lose. Okay? And we know that sodium's it's easier for it to lose that 1 than to gain those 7. So chlorine needs 1 more electron to be stable, and sodium needs to lose 1 electron to be stable, to have that full inner shell. So that electron will go to chlorine. And now chlorine and sodium are going to be bonded. This is going to have a negative charge. This will have a positive charge. And now I can make that compound. And now we write it out. So first I'm going to write out my oxidation numbers. Did chlorine gain or lose electrons? Chlorine gained. So for me to do that, I'm going to have to write a 1 minus or a Cl minus. Okay, that means that it has 1 electron than normal. I look at sodium. Did it gain or lose? Sodium lost an electron, so sodium's now more positive. So I'm going to be more positive by 1, and I can get rid of this 1 and just do a plus if I wanted to. So now this is saying I have 1 more proton, or I have 1 less electron than protons. So I write out my oxidation numbers. Okay, this formula is not correct. I'm going to tell you how to do that here in a second. But I'm just showing you right now your oxidation numbers that you need to write. So now I have a compound that's neutral and stable. I'm balancing each other out. So I have what's called a net charge, a 0 net charge. They're going to neutralize each other. And this neutralization is going to be the pull that has these atoms come together. So when we write them out, though, we have to write them out a very specific way. We have to have cations come before your anions. So I have to write my compound very specifically. The cations, remember, the cations are positive. So which one of these is my positive one? It's my sodium. Okay, so sodium will go down first, and then my anion will go next. So I will write out NaCl. I got to show my charge, my oxidation number. So I would do a plus and a minus. This is showing this is an ionic bond and that I have a pull together in this bond due to these charges. Okay, so now let's look at calcium and oxygen. We're going to kind of draw out an ionic bond. So first thing we want to do is do our Lewis dots. So you find them on the periodic table and you figure out how many valence electrons they have. Calcium's in group 2, so it has 2. Oxygen is in group 6, so I have 6. So now you have to ask, all right, is it easier for calcium to get rid of 2 or for oxygen to gain 2? And it's going to be easier for oxygen to gain. So calcium is going to go and it's going to share, or not share, it's going to give its electrons to oxygen. So now oxygen has these 2 electrons. Calcium no longer has those electrons. So now I got to figure out my charge. What charge is oxygen and calcium going to have? So I'm going to be -2 because I've gained 2 electrons. I'm going to be +2 because I lost 2 electrons. So now I have to write it out. Which one of these are my cations? My positive. Okay, so calcium is going to go first, and then oxygen will go next. So I write it out just like this. Ca2+, O2-. All right, let's try a little harder one now. This is our last practice. Okay, I've got magnesium and chlorine. I want you to take a second and try this one out and see if you can kind of do it on your own. All right, so magnesium and chlorine, let's do our Lewis dots. I have magnesium in group 12, chlorine in group 7. All right, magnesium has 2 valence electrons. Chlorine has 7. So chlorine only needs 1. So chlorine needs 1, and I can only bring in one of these electrons. So if I bring in this one, magnesium's not happy. Chlorine's happy, it's got its 7, but this magnesium's not happy yet. What could I do to help get rid of this other 1 electron? What do you think else? What else could be attracted to this 1 electron? A second chlorine can. So what happens is you're going to have this one come here, and then this one is going to be attracted to another chlorine atom, and so another chlorine atom is going to come along and it's going to take this electron and put it here. All right, this is where I need you guys to pay attention, because this is where you guys like to mess up and write something very different. So how many electrons did this 1 magnesium lose? It lost 2. So my charge is going to be 2+. I lost 2 electrons. How many electrons did this 1 chlorine, just this one, how many electrons did this 1 chlorine gain? It gained 1. This 1 chlorine gained 1. So this is going to be a -1. How many did this one gain? It gained 1. So this one is also -1. But when I write out my formula, I need to show I have 2. Do you remember what it's called, that number that I write at the bottom that tells me I have 2 chlorines? It's my subscript. So when I write it out, I have to write it out like this. So magnesium lost 2 electrons is 2+. Each individual chlorine gained 1 electron, but I had 2 of them. What you guys want to do is do Cl2-, and that's saying that that 1 chlorine gained 2. But that's not what happened. I brought in 2 chlorines, so I have to show that with a subscript of 2. And each individual chlorine only gained 1 electron. They didn't gain 2 each. They only gained 1. So we have to show it like that. And when I cross multiply here, they cancel out, my charges neutralize. And so that tells me that I'm pretty good with what I'm doing. All right, that's kind of a harder one. You have to kind of predict what you're going to do. All right, so now my compound is now neutral and stable. All right, that's ionic bonds. I hope that was helpful. If it was, let me know. If you have any questions, let me know that too. I'll talk to you guys later. Bye.